Hello, hello. Continuing on in Chapter 6, Lecture 14, we're going to look at learning objective number 4, the last for this particular lecture. We're going to be looking at our faults within the idea of using light as a wave, so bringing into the idea of wave as, or light as a particle as well. So what is it that caused scientists to be like, okay, obviously light is not just a wave, it must actually also act as a particle. So we're going to be looking at our line spectra, we're going to be looking at black body radiation, stuff like that. So our wave model fails when thinking about black body radiation, the photoelectric effect, and the idea of emission spectra of elements. So our line spectra. So black body radiation is hot objects emit light, like our sun. The photoelectric effect, here light is ejected, or light causes the ejection of electrons from a metal. And then our emission spectrum, specifically line spectra. So if we have an electrically charged gas, it will emit light in characteristic lines. Okay, so these phenomena cannot be explained using the idea of light as a wave. So an alternative explanation was determined. And that's that light acts as a particle. And that particle is a little packet of energy known as a photon. So this is our particle model of light. So let's look at each of the different things that actually caused this disagreement and resulted in the theory of light as a photon or packet of particle. So blackbody radiation, this is that anything that is hot enough is going to emit light. We can think about the sun like this. So the sun emits light. You can think about a flame. Flames have different colors based on what temperature they are. If you've ever taken a pot and you've put it on the stove and cranked it up real high, it can glow red. So all of these things are examples of black body radiation. So an object is going to absorb the radiation falling on it, all wavelengths. This is called a black body. So a black body is an object that absorbs all radiation falling on it at all wavelengths. We can kind of think about wearing a black shirt when we're thinking about a black body. If you've ever worn a black shirt, you know it's going to absorb all that radiation and you're going to warm up. So absorbing that radiation increases heat. And then if we think about a black body radiator, so if a black body is at a uniform temperature and that temperature is high enough, it's going to have an emission that is characteristic upon the temperature. That's going to be a hot temperature. This will have a characteristic frequency or wavelength distribution. And that is dependent on its temperature. And that is that emission of a black body is what we call black body radiation. So black body radiation is you heat something up, it emits light. A black body, it absorbs light and heats up. So you can kind of think about it that way. So objects are going to glow when the temperature is increased. Okay. If we have a heated solid, they're going to emit radiation. And that light or color of light depends on the temperature. So we have something called a color coordinate diagram. It kind of looks like this, where over here is blue, here is red, and up here is green. And you can look right here, there's a little line, and on here are several different temperatures, which are based on black body radiation. Right in the center is white. So an LED light, you will overlap green, red, and blue to produce white light. And this is kind of where this comes from. So it comes from the idea that um, a black body radiator at a specific temperature will have a specific color, and then the overlap of green, red, and blue gives us white. So look over here, we go from red, we go into an orangey color about here, then we go into white, there's some yellow, sorry, there's yellow right here, white, and then blue. So this is our lowest temperature over here. And as we increase our temperature, so we're going to increase temperature in this direction. So increase in temperature. So we would say that red is hot, but as we go along this color coordinate diagram, we continue getting hotter. So a red emission is a fairly hot emission. Yellow is hotter. White is even hotter. And then blue is actually going to be our hottest temperature. So something that is really, really, really hot is going to emit blue. Um, so it has nothing to do with intensity, only on temperature. So we can have different intensities, but the same temperature will give you the same light. So intensity of light is not the amount of energy, it is the amount of photons. Okay, so our energy or wavelength gives us our color. Our intensity is just how many of those photons you have at a specific energy. Okay, so this was not able to be explained using modern physics at the time. So we have a guy named Max Planck, or Planck, who is a German physicist. And he's the first one that came up with this idea of energy being absorbed or released in discrete chunks or minimum size. So he called this chunk a quantum. And he said that um, different things will have a smallest quantity of energy that has to be absorbed or emitted, and he called that the quantum. So the quantum is the smallest quantity, quantum quantity, of energy emitted or absorbed as electromagnetic radiation. So from here, we've already talked about the idea of Planck's constant, but this is where he actually came up with this constant because of the idea of a quantum. So We have our Planck's constant. (6.626 times 10 to the negative 34 joules times by seconds. So he got this from the idea of quantum. So relating that energy um, with what can actually be absorbed. So a quantum is a fixed amount of energy. Okay, and we can determine the energy of that quantum using our energy versus frequency equation. So the energy of it is equal to Planck's constant times by frequency. So an atom itself can only absorb or emit whole number ratios of those quantums. So they can absorb one quantum or two quantums or what have you. So this gives us the idea that energy is quantized. So unlike what they thought before, it doesn't depend on the intensity. You can't have an atom that will absorb energy just by increasing the intensity of light. You have to have a minimum threshold in order for that energy to be absorbed, and that gives us the idea of that quantum. So if we think about a quantum and we compare it to something like continuous, so if we want to compare quantized versus continuous, we can think about so if an atom if the energy within an atom, or the energy that an atom could absorb, was continuous, then it can absorb energy anywhere. Sorry, it can absorb any amount of energy. So we can think about it like a ramp. But that's not what we find. We can't just add a little bit of energy and get absorption of that energy by an atom. We actually have to add in a set amount, or a quantum, in order for that atom to be able to absorb that energy. And that amount depends on the atom. So here we have only specific amounts of energy being able to be absorbed or emitted. So once we've reached this quantum threshold, we can absorb energy by an atom. If we have greater than that, if we add in greater than that amount, but still less than this amount, for instance, then we'd only absorb energy to here. So there are specific set values that an energy or energy can be absorbed from a photon by an atom. Okay, next we have our photoelectric effect. So here, a light, we've got a clean piece of metal. Light is shown on that, and electrons are ejected from the surface. So that's our photoelectric effect. We have to have a clean metal surface. So when light is shown on a clean metal surface, electrons are ejected from the surface. Now, again, intensity does not matter, or it does, but we still have to reach a minimum frequency for this phenomenon to be observed. So there's a minimum frequency of light that must be applied in order for this phenomenon to be observed. Okay, so our intensity does not matter. Our intensity does not determine the minimum amount of energy. If you have a set amount of energy, if we've reached that threshold, that minimum frequency of light, then the amount of photons of light that you put on will increase the number of electrons that are ejected, but you still have to reach that minimum. So the minimum must be met first, and it's going to be dependent on the metal. So it varies according to the metal. Okay, and the intensity will only affect the amount of electrons. That can be ejected, not whether or not they will be ejected. Okay. So we at this point have a quantum, and now we have Albert Einstein, who was able to explain the photoelectric effect. And he's the one who coined the term photon. So he postulated that the radiant energy striking the metal surface acts like a tiny packet of energy. So here, um, if you have a photon of light and it reaches that minimum of energy, then that one photon can transfer its energy to one electron. And as I said, if we've reached that minimum energy, that will eject the electron. If we have not, then it will not. He coined this packet of energy, the term photon. So he coined the term photon. That is our packet of energy that acts as a particle of energy. And of course, he gave the energy of this. E photon is equal to Planck's constant times by frequency. So this is our quantized radiant energy. So when you think about a photon, it is a packet of energy. So as such, the higher frequency, the higher the energy. And when a photon interacts with an electron, it can either cause that electron to go into an excited state, or it can cause ionization. So we can either have an excitation of an electron from a lower energy state to a higher energy state. So this is the absorption of energy. The other thing we can have is the electron can be ejected if enough energy is added. Or let's go with if the photon of the energy of the photon is great enough. So this, we call this ionization. This is how we produce cations. So that minimum energy to eject an electron from an atom is called the work function. Okay, so we call that work function the minimum energy to cause the ejection of an electron from a solid. Almost always we're looking at metals in here. And this causes ionization. So forming that cation. So the type of the atom and the location of electron in reference to the nucleus will determine the work function. Okay. And again, note that all the energy of one photon will be transferred to just one electron. Okay, so if that energy is not great enough to cause the ejection, you can't add another photon in to cause that ejection. Okay, the last thing I want to talk about is the idea of the line spectra. So talked about our photoelectric effect, talked about black body radiation. Now we're going to talk about line spectra. So first, before we talk about line spectra, I want you guys to be aware of our types of light. So our light can be monochromatic. So made up of one wavelength. And so single photon. This is something like a green laser pointer. Or it can be polychromatic. That's what we almost always look at. So it's made up of multiple wavelengths. So overlapping wavelengths. And what we observe is the sum of those overlapping wavelengths. For instance, if we have white light is actually a combination of red plus green plus blue. So if we have polychromatic light, we can take that polychromatic light and separate it through a prism. So we take light source and we put it through a slit. So we have a very thin thing of light coming through, and then that is then placed in a prism. Like so. And when it's placed in the prism, it's going to spread out into its composite wavelengths, and this is called a spectrum. So our spectrum is polychromatic light separated into its component wavelengths. Okay. Now, if you look at the spectrum and you see that it is continuous, so it looks kind of like a rainbow, um, we call it a continuous spectrum. So a continuous spectrum, like a rainbow, is going to be one where there are no or very few breaks in the colors or in the light. We'll go with in the wavelengths. However, we can also have what's called a line spectrum, where all the wavelengths are single, or all the colors or wavelengths are just single wavelength lines. So here we have single wavelength lines. Most of the things we look at are continuous, but line spectra are special, and that's what we see when we look at atoms. So when you take an atom and you excite it, so a single atom, hydrogen or neon or something like that. So if you excite an atom or molecule in its elemental form, the wavelengths of light it will exhibit will be based on the element. So each element has its own characteristic spectrum, and it will be a line spectrum. So if we looked at a compound, looked at wavelength versus intensity, we'd have something that looks like this. So this would be continuous. So there are few or no breaks in the wavelength emission once we put that through a spectrum. If we were to look at an atom, such as hydrogen, we would have lines. Instead of a big broad peak of wavelengths. And this again was not really able to be explained by the idea of a molecule, or sorry, of light acting as a wave. So, starting out, researchers were looking at the hydrogen spectrum. So they saw this, they saw these lines, and every time they saw the same lines. 410, 434, 486, and 656. So these four lines showed up every time. There were a few lines in the ultraviolet and infrared regions as well, but they weren't discovered at first because they're not visible lines. So, hydrogen, they saw that it exhibited this line spectra, which did not make sense to them. So they started looking into this, and we have Johann Balmer tried to explain this and instead came up with an equation that related the hydrogen emission lines to integers. Emission lines. Okay, and when he found that 1 over wavelength is equal to the Rydberg constant times by 1 over n1 squared minus 1 over n2 squared, where our Rydberg constant is 1.096776 times 10 to the 7 meters minus 1. And using this equation, n2 has to be greater than n1. So this equation is for hydrogen specifically. But this was later revised to relate all elements and their line spectra. So the question then became is why does this work? How are we able to get these integer values? And along came Bohr. So Bohr, Niels Bohr specifically, he was the first person to explain what's going on with the line spectra of atoms. Starting out with hydrogen. So he had his hydrogen model. So he developed the Bohr's hydrogen model. Okay. So he had three postulates, and within there he brought in the idea of quantized energy for an atom. Okay, so prior to this, there was an orbital description of an atom, so electrons orbit the nucleus, but that did not explain this line spectra. So instead of a orbital description of a nucleus, or orbital description of electrons. Okay, so his postulates: only orbits of a certain radii corresponding to a specific energy are permitted for the electrons of a hydrogen atom. The electron of a hydrogen atom. Okay. Then an electron in a permitted orbit is in an allowed energy state. So our electrons themselves are not allowed in any unallowed state. So an electron not in an allowed state would radiate energy, but an electron in an allowed energy state does not radiate energy. And that's good, because if it radiated energy, it would spiral into the nucleus. And then energy is emitted or absorbed by the electron only as the electron changes from one allowed energy state to another. So we can't absorb energy if you can't go from one allowed energy state to another energy state. So this idea that if you take an electron in a lower energy state, you add enough energy to get it to a higher energy state, then that electron is allowed to absorb that energy. And then when it goes from that higher energy state back down to that lower energy state, it's going to emit that energy that it had initially absorbed. And of course, the energy is absorbed or emitted as a photon, and that photon has energy equal to h nu. Usually. An atom can also absorb or emit phonons, as a note. So phonons, these are heat. So it doesn't have to be light, it can also be heat. Heat can cause the excitation of an electron or the emission of energy from an electron to go down to a lower energy state can be in the form of a phonon instead of just a photon. Okay, we are nearly done here. So our hydrogen atom orbital energies, so the energies of the orbitals for the electrons, so those allowed energy states, are given by E is equal to hc Rydberg constant 1 over n squared, or E is equal to, sorry, there's a negative 2.18 times 10 to the negative 18 joules. So if we multiply all this together, we get that. 1 over n squared. So again, that n, that's the integer value. So n equal 1, 2, 3, so on and so on until infinity. This n has become known as the principal quantum number. Okay? And it gives the energy of the electron, or we can also call it the energy of the allowed energy state. So whatever energy state that electron is in that has the same energy as the um, state itself. Okay, so our principal quantum number, if we think about n equals 1, that's going to be the smallest, and it's going to increase as we go up. So it'll go from n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, n equals 6. And as we go up away from this first energy level, the first energy level, by the way, is the one that's closest to the nucleus. So if we have electrons in that n equals 1 level, energy level, those are going to be closest to the nucleus. As we go from n equals 1 to n equals 2, that's a fairly large jump, but going from n equals 2 to n equals 3 decreases, and it decreases on and on and on until we reach infinity. Okay, so n equals infinity, and actually I'm going to so these are energy levels within a hydrogen atom, and we can excite electrons in between any one of these energy levels. So our energy goes up as we go in this direction until we reach this point right here. We actually call this our 0 point. When we reach our 0 point of n equals infinity, we have ejected an electron. So this is our work function. Okay, so our n equals 1 is our lowest energy state, the one that's closest to our nucleus. And it's the one that is furthest away from this n equals 0 state, so the hardest electrons to remove from the atom. So lowest energy, but hardest to remove from the atom. When we take an electron from any one of these states and we take it to a higher state, we say that it has been excited. So if we go from a ground state, which is the state that the electron is in at the lowest energy level, so our lowest energy level, we can then excite it and get to an excited level. That is everything for today. We will continue on our next one. Bye.